So welcome to the Software and Computing Roundtable of April 5th. The topic of this month is experiments starting up. So we are in particular interested today in the interplay of development and operations. We have 4 presentations today. So we will hear from 2 experiments at CERN. David Rohr and Rosen Matev will talk about ELISE and LHCb. We will hear from a neutrino experiment. Timm from FNAL will talk about preparations for DUNE. And we will start with a nuclear physics experiment at RIC, the sPHENIX experiment. Like usual, after the presentations, we have about 5 minutes for questions. Please free to either raise your hand or put the questions in the live notes. I will share the link to the live notes in a second. But before I do that, I stop my share and I give the screen to Chris Pinkenburg from Brookhaven, who will give us an update on sPHENIX starting up. I see your slides, not yet full screen.
Yeah. Yeah, at least it started back up without a problem, so that's good.
Perfect. It's all yours, Chris. Go ahead.
All right. So thank you for giving me the opportunity to talk about sPHENIX here. So as Marcus mentioned, so sPHENIX is a new experiment at the Relativistic Heavy Ion Collider here in Brookhaven. And as you can see, we're going to take data in 322 days, which is something like 10 months. So 21st of February is currently the target date. Naturally, the experiment has been coming for a long time, and I looked a bit through the history, and this is actually where we started. Pretty much 10 years ago in Boulder, sitting together in the computing corner and hacking up the simulations and basically trying to design a next generation heavy ion detector for RIC. Then politics kicks in, so our bigwigs got this thing into the long range plan in 2015 as one of the goals for the next 10 years. Collaboration was formed in 2016. In the meantime, we have more than 320 members, 84 institutions, 14 countries. And on the right, you see that was kind of the founding of sPHENIX. Again, in the meantime, we are quite a lot more. So what are we actually trying to do? So what we are looking for is jet measurements at RIC to probe the QGP, learn something about the inner workings of the QGP, understand it. We want to look into apparent energy loss, which means you basically look at different quarks. So at RIC, we can see UD, SC, and the B quark. Top quark is inaccessible to us, but we can look at epsilon, so we can look at the B quarks. And we can basically look at size difference. So we can use epsilon as kind of a thermometer. So what our detector needs to do in this slide, this is what it needs to do. It has to be able to measure jets. So we have calorimetry. We have full hadronic calorimetry. It's the first time that at RIC you actually have a full hadronic calorimeter. You need electromagnetic calorimetry. For the momentum for the epsilons, you need a magnet, and you need a tracking system. Our tracking system is a time projection chamber. Inside the time projection chamber is a map space vertex detector or vertex tracker. We want to resolve B jets. We want to look at the B's in there. And then we have an additional intermediate silicon tracker. The reason for that is it naturally gives us an additional space point. But the main reason is that this actually nails a track down to a certain bunch crossing. So the other detectors, integrate over multiple bunch crossings, and this INTT will basically tell us from which bunch crossing a track came. In terms of performance, we're going to take data at a high rate, so 15 kilohertz readout rate for all the sub-detectors. And as you can see from the acceptance, it's a typical collider detector, in coverage, eta, pseudo rapidity, smaller 1.1, and all of 2 pi. Triggers, that's actually what, hello? Okay. Triggers, that's actually something which makes sPHENIX stand out among all its peers, what we're going to do, we're going to only use level 1 triggers. So we don't have any high level triggers. And but that also means that for us, there is no need to actually build every single event online, which is the reason why we punt this into offline. It's much simpler if you can do this offline. So basically, in a nutshell, we are basically designed to take a ton of min-bias data in a very short period of time. We have a running period of about 3 years, according to plan. So what are we actually looking at? On the right, you can on the left, you see the projections for years 1 to for our 3 running years, and on the right, you can really see the counts what we expect. And after 3 years of running, you expect, with these rates, 2,400, direct photons above 30 GeV. So we are dealing, in the end, we're dealing with very, very small numbers out of a huge amount of incoming data. Why do we do this? We actually have a chance, especially for the jet physics at the bottom, we actually have a chance to bridge the gap between RHIC and LHC. You can see with our measurements, labeled here as RHIC tomorrow, which means us, we actually overlap with the low end of the LHC experiments. So that gives us really a nice, in the end, what we are shooting for is some kind of excitation function, which basically goes from RHIC up to the LHC experiments, which will give us a good and basically a better understanding of the QGP. This is our 3-year run plan. So in year 1, next year, naturally, we have to commission the detector. It's brand new, has never seen beam. So we give us a couple of weeks for the commissioning, and then a shortish gold run where we have to reproduce the standard candles at RHIC. We have to reproduce the RAA, previous measurements, basically see if we are in line with what's been known so far. Year 2 is then the PP run, so heavy ion data. For people who are not familiar with it, you live by comparing to PP data. So without the PP reference, the heavy ion data is pretty much useless. So in year 2, we're going to take the PP reference from. And since it's RHIC, polarized protons, we also get some nice, cold QCD, spin physics out of this one. And then year 3, this is going to be our very large gold heavy ion run, where we then really go for the jet and the heavy flavor physics. In total, we shoot to collect 140 billion events. What's like 300 petabytes of data. And that will give us then the capability to match up with the LHC experiments in terms of analysis. Progress, it's been, we were not that badly affected by COVID, interestingly enough. I haven't been at Brookhaven for 2 years, and I left, the IR was empty, and when I come back, I'm basically seeing this here. So the magnet and the outer HCAL and the REC platform as of last week is now installed in at IP8. We have the inner HCAL the barrel is complete, and it's now ready that we install the EMCAL inside it. So what you see on the right side is the contraption with which the EMCAL sectors can be installed inside the inner HCAL. Now let's start with the software with the nuts and bolts. So data acquisition. As I already said, the data acquisition system for sPHENIX, we are rate limited to 15 kilohertz. That's a design choice. It's given by the front end. So that basically means we get the same event rate in PP and in gold. The size of the data set will be different, but not the number of events. Initially, when we did the calculations, we had a tremendous amount of background. We would have had to deal with 200 kilohertz of collisions in the TPC, while the number of useful collisions inside our vertex detector, which is plus minus 10 centimeters, is around 30 kilohertz in the beginning. So what we will employ is a small angle, crossing angle, which will reduce the rate of these off-center collisions by many factors, which basically gets us into a range where we can handle the TPC data. The problem, as I pointed here, the TPC will see the full rate. So if the collision is outside plus minus 10 centimeters, the particles still make it into the TPC. Yeah. But nevertheless, even at these rates, we will have pileup in the TPC. There will be multiple events in there. And we will have space charge in the TPC, which then will distort the tracks, and we need to deal with that. And another thing which not too many experiments encounter is that Rick has 20 years of experience. They are really good in getting luminosity out of their machine by now. So the collider operations will reach their peak luminosity pretty much on day one. Unlike other experiments where you ramp up the detectors and the collider at the same time, we don't have this luxury. We will basically get blasted on day one with with a very experienced collider. FNAL data acquisition. So that's so you have on the left, we have two types of readouts. You can see on the left, we have the colorimeters and the MBD. That's our minimum bias detector. It's just a collision detector, Cherenkov counter around the beam pipe. The data gets routed out by front-end modules, which then get transferred into DCM's data collection module. We have in the meantime version 2. This is why they're called DCM version 2. From there, it goes into a sub-event buffer. And other experiments would then put an event builder behind this. We don't do that. We just feed this through a network switch into something we call the buffer boxes. These are just nodes with lots of disk space, which allows us to write out outages, for example, or where you reduce the incoming rate, which at the beginning of the store is extremely high and then tapers off. And between fills, you don't have any data at all. So it reduces the instantaneous rate to an average rate, which we can then send to the computing center for storage, for archiving and processing. On the lower left side, you see these are our tracking detectors. That's the TPC, the vertex detector, and the INTT. Again, they have goes read out via some front-end modules. That data gets into a FNAL card. That's a neat device from Atlas, and gets assembled there, and then also sent to HPSS. So as you can see, we've got 20 calorimeter files and about 40 files from the tracking system. So all of them get sent, separately into archiving. Naturally, we have 60 files. So just as a proof of principle, what you need to do is that you have to actually produce some fake up data. And Martin did that 500 million events in 200 runs. Producing basically the sub-event files the same way that via real data acquisition processes, and then combine them with our event combiner, and check if that actually adds up. And so our software can handle that. So we can actually assemble these files with sub events later on into real events with we have got all the safety belts in place, which allows us to make sure that there's no data corruption on the way.
Chris, this is your 10-minute warning.
Oh, okay. So we have two classes of events. As I said, we have got the triggered readout and the streaming readout for the inner tracker. So now what do we do with the streaming readout? So on the upper bar, you see that's basically the streaming readout. So you just get continuous stream of data. What then happens in the FNAL card is that the FNAL card cuts out the chunks of data which correlate to a trigger and only copies those data out. But what we can do now, employ, is we can actually add some opportunistic streaming only data. So if you see at the bottom, so the top is basically the must-have stuff from the TPC. So basically the time sequence, the sequence which contains the event you're interested in. But if you then read out, a few more, couple more, 10% more of the data afterwards, you actually pick up more events in the TPC. So this would allow us to increase the sample of events we can analyze in proton-proton. So if we do this here in proton-proton by just increasing the basically adding 10% of the basically streaming 10% more than what we need to, we get the data volume increases by about 50%, but we get about an order, 2 orders to 3 orders of magnitude more PP events. So we get a really treasure chest of, these events are truly unbiased. Yeah? They were just randomly taken. There's no trigger for these events. So we can get a treasure chest of really truly unbiased PP events at a marginal price increase. Data event and data volume, CERN run 1 in the gold run, it's 13 weeks. We shoot for 43 billion events, it's 72 petabytes. PP, we run longer, 21 weeks, so 69 billion events. That's PP and OKP gold. Since the events are smaller, it's going to be about 78 petabytes. But now, if we do this 10% increase, this 10% increase, so we would take about 100 petabytes of data. Run 3 is then our big gold run. That's 100 billion events, and that's going to be about 180 petabytes of data. Yeah. So I'm now switching to the software. So we are a very small core group. So that means basically, you use what you already have. So there's no manpower for, reinventing wheels. If you look at Phoenix, where we come from, it took data at 6 kilohertz. And it certainly, the detector was much more complicated than we have now. So we are we have experience with these kind of things. And in addition, since we have a small core group, students will write most of the code. So we basically stay away from fancy, all this, look what I can do. We really try to, it basically ends at STL containers. We don't really do anything with templates or anything where a student would take weeks to get going with. We don't reinvent the wheel, as I said. We use existing modern tools. For the tracking, we use ACTS, KF particle for the heavy flavor, the conditions database from Bell 2, and Panda for workflow management. As I said, we have very short commissioning. It's a new detector, and we have a couple of weeks to get this to work. So the flexibility of our software framework is really key, that you can put in new things and remove stuff, linking against third-party libraries without having to, restructure major parts of your framework. And yeah, we got tons of help from other experiments. So just mentioning Alice, the CA seeding from Alice, Atlas, ACTS, STAR, the collaborative software. Thanks a lot. That was extremely helpful, and we're looking forward to get more help. A nice feature what we have is that our events are actually time ordered. Yeah? So the sub events come out of the DAC in time order, and we write them directly like this into mass storage. Yeah? So we don't have this problem other experiments have, which run an event builder then on multiple nodes, where then your event numbers get scrambled. Yeah? Which makes the reconstruction, calibrations, and synchronization of multiple streams a lot easier, because you know exactly where the next event comes. And especially for calibrations, really allows us to calibrate up to a certain event. So we can say up to this event, this calibration is valid, from the next event, then on the next one. So deployment.
5 minutes.
Yeah, okay. Code is in GitHub. Pull requests trigger really extensive CI, including QA. It's run in SDCC, so we don't use the GitHub actions because, if you really want to run something there, it costs serious money very quickly. So it addresses the, when did we lose this 10% momentum resolution, which is something which happens occasionally. We have singularity in Docker containers with the SDCC farm image, and our software, we have daily and tag archival builds there in CVMFS, and we have daily builds with multiple compilers, and that basically ensures that our software is kind of C++ compliant. So you're not targeting a special compiler for your stuff. Let me a few words of to the sPHENIX tracking. So in the meantime, that has grown from a simple, take some hits and then have the tracking run over that to some really intricate workflow scheme. We've set ourselves basically a target of 5 seconds per event for tracking pass. So that means 10 seconds per event for both. We have 2 tracking passes. Both passes, so that's the goal. We're almost there, and 4 GB per job. Both of that is within reach. Here are some performance plots, so the performance meets our physics requirements, so that's good. Yeah. Multi-threading, we always get asked, why don't we use multi-threading? And in heavy ion physics, most of the memory is actually consumed inside the event, so it's event data. So multi-threading on an event-by-event basis, it doesn't really help you too much. In PP it does, but not in heavy iron events. But what we can do multi-threading inside an event loop. And that actually does look promising. So on the upper right, that's for the TPC class string is multi-threaded. At the lower left is the MCAL, the pulse fitting, running as function of the number of threads. And we also have a little an effort doing pulse fitting with machine learning. Problem what we noticed that it relies on nodes that actually having spare cycles. So the better you make use of a CPU, the less the multi-threading actually helps you. And we need to look into it. So we are running a mock data challenge and what you see on the right side is basically we set it up in a way that we can really run our real data reconstruction as part of it. So that's what you see on the right side. It's tracking and calorimeter clustering. And then, a higher level reconstruction like particle flow jet reconstruction, and then people can do physics with that. There's no truth information involved. The truth information is separated early on, can be combined afterwards in the analysis, but that takes active action to do that. Our production workflow we are thinking currently is that we want to employ some pre-processing of the calorimeter file, so we get a head start there. And that actually helps us that we have the data in separate files, because now you can basically just open, just only the files which contain calorimeter data and process them. So you don't have to, look at the tracking data. So we get about a 75% data reduction there. That's really helpful. And then we feed the output of that in the calorimeter clustering. On the tracking side, the TPC clustering, you basically have to read all the data in. So there we will have to read 40 files, do our 2-pass tracking, and basically write then the analysis output back to HPSS. Calibrations, just it's complicated. We have 2 types of calibrations dealing with the distortion corrections. They are outside of the conditions database. They are very short-lived, or they cover very short periods of time. And the first tracking job produces the calibration the second tracking job needs. So there's a one-to-one match, so we don't have to have any database behind that to organize that. Yeah. Space charge distortions, I think David's probably going to say something about that. That's a real problem for the TPC. So we have 3 ways to deal with that. We have a direct laser just to get static distortions, which means the magnetic field, for example, distorting the electron drift path. That's something you run, in between at the beginning of the run, or in between in beam breaks. You don't expect this to change. That's a static distortion. We have a diffuse laser, which basically where we produce electron clouds during data taking, which then drift towards the path plane. We read it out, and then from their path, you put in a known pattern, and you can basically see how the integral distortion is. We added a different another detector for getting out in some areas of the TPC an outer space point, which then again helps us to look at the distortion in these areas. I'm almost done. So data flow is really the name of the game. So basically, what sPHENIX faces is scale. It's a problem of scale. If you just do the numbers, so our CPU estimate is about 25 seconds per event. That's where we want to be, and we are close to that. We want to run 2 reconstruction passes, one really near time doing data taking, within a day or something, and then offline, between rig runs. We've got another half a year. If you just do the math, 107 billion gold events in 24 weeks at 25 seconds per event, that means we need 184,000 cores to just run this. So we cannot afford idling cores in this scenario. Sadly, the speed of the construction is not just the speed of the job. You basically have to start it up, and you have to get the data to the job. So and cores do idle during data copying. And we have to get everything to a 10 gigabyte per second network. So we will need to work on your prefetch post-processing copy schemes. Basically what you need to do, you have to keep the cores busy. And this is where NPVS comes in helpful. So we're going to use Panda, and I love that. So you see, they probably look at the problem they are facing. So it's Shrek and Rukio. Jason Webb spearheading this. So we're going to use our mock data challenge to exercise this thing. So far we can run the first pass, so creating the files and running the Gen4 simulations. Rookie is almost on board, so that's interface that's going to happen next. And then we can actually run this mock data challenge under Panda, and then we can start really exercising the system and dealing then, improving the workflow. So summary, we do plan near-time full reconstruction, followed by a second offline pass. The processing time per event we envision is well within reach, so that again, we don't expect any issues there. We actually just pat ourselves on the back. We accomplished the 2 orders of magnitude speed increase. If you look at 3 years ago, we were at like 20 minutes per event. So thanks a lot to ACTS. That was the breakthrough there. We use tools from the wider community, so Panda and Rukio playing nicely together. They're going to do our workflow management. We got the conditions database from Bell 2. In the meantime, it's implemented, works nicely. It does exactly what we needed to do. The big remaining challenge is really the data flow. And we are running this ongoing mock data challenge, for testing, developing these scenarios and testing it. And yeah, last not least, if you look what comes after sPHENIX, ERC is on the horizon. So some of that is probably gonna be the guinea pig for the ERC. And if you look at the computing challenge, it's likely sPHENIX needs more computing than ERC. Our events are much more complicated, and the reconstruction takes somewhat longer. And that's it.
Thank you very much for this excellent summary of the preparations for sPHENIX. We have one question. Liz, please.
Yes, you mentioned the time per event, but what is your memory? When you ask for memory from the batch system, how much do you have to ask for?
So what we basically get dedicated hardware for it, so it's 4 gigabytes per core. Yeah? So our jobs right now they need 6, but we have ideas how to shave it off, so we'll get it below 4. Initially, most farms have 2 gigabytes per core, and that was hopeless from the beginning. You just look at it's like there's just no way you can fit a heavy iron event into that kind of memory.
Okay, thanks.
I don't see any question in the chat. So something which you mentioned at the beginning of your talk, Chris, was that you really have only 3 years of running, and you expect that rig will really be able to start within 1 day and you can keep going. What are the preparations which you have done on the software and computing side to be ready from a commissioning point of view? Is this mainly your data challenge coming up where you test your data flow, or are there also other things like already starting with some calibrations, etc.?
Yeah. I skipped over the calibrations. So yes, the calibration is a hot topic right now. I mean, the space charge corrections is one issue, but also calorimeters. We need alignment. We need many more calibrations that's actively being worked on. What naturally comes next is we have to start monitoring the detector. Also developing monitoring procedures or monitoring software for the detector, where this is actually an interesting problem because, again, we basically get only sub-events. So we will have to combine some events online just to see, you have to see if if the data still lines up, if your counters are still line up, or if you lost something on the way there, which then scrambles all your data. So that's probably going to come, in a month or two. We're going to have, a big get together, and then see how we actually want to organize the monitoring.
So the year to the start will be really busy.
Yep.
Okay.
It is already, yeah. So yeah. I mean, the good news, I mean, as you can see, the detector is well on its way of being assembled. So that frees up quite a lot of manpower for students who then can be put onto software tasks. Which brings me back to, the software must not be too complicated, so students can get into it, very quickly. That they have to.
Yeah. No, thank you very much, Chris. I would have a couple of more questions, like asking you more details about your speed up of the reconstruction, etc. But we have, unfortunately or fortunately, more talks coming up. So we look at this from experiments starting up from many perspectives. So thank you very much, Chris. And we go to the next presentation. And now we go from heavy ion to complete different field, neutrino physics, a particular accelerator-based neutrino physics, DUNE, new flagship experiments coming up at FEMILab. And Steve, Timm will share with us their work and on getting ready for DUNE. Steve, would you like to have a 5 or 10 minutes warnings or both? You are muted in case.
5-minute warning will be good.
Okay, I will give you a 5 minutes warning. So thank you very much. The floor is all yours. Go ahead.
Good morning, everyone. You see the world map with data transfers moving from Fermilab via Ruscio to a bunch of other places. We have a global computing infrastructure already. Why do we do DUNE? Because we need precision measurements of the neutrino mixing angles. Most of you may know that there are 3 flavors of neutrinos as seen by the weak interaction. Those are 3 mixtures of mass eigenstates, and we want to measure all that mixing in the same experiment, plus the cross-section, plus the mass hierarchy, and plus when you have a detector this big and this far underground, it's also ideal for neutrino astrophysics such as supernovas, and also good for looking for nucleon decay. That is, in fact, how we all got started in this game of doing big neutrino detectors. I'll cover an introduction to DUNE, the data formats, RICO analysis, computer infrastructure, workflow and data management, and then some conclusions. So we start with an almost pure new mu beam at Fermilab, but over time and over distance, it will oscillate. So you start with the blue, it will be all new, pure new mu as we leave, almost pure mu. You see black is new E coming across, and then you see new tau coming up. But in fact, DUNE is looking only for appearance of new E at our normal energy. The mean energy of our beam is approximately 2 GeV when it gets to the mine. So we create a very, very high intensity neutrino beam at Fermilab, send it underground 800 miles or 1,300 kilometers to the Homestake mine, or what used to be the Homestake mine is now the SURF, Stanford Underground Research Facility in South Dakota. It's an old gold mine. We are 4,800 feet underground, almost a mile. And there are actually caverns now being dug for the detector. For scale, one module of the fire detector is about the same as a big university physics building for scale. And probably we've got one hole dug all the way through this cavern. In fact, we've got one hole dug all the way through all 3 caverns that we will need. And so a hole is getting dug in South Dakota, and detectors are being made to go into it. So we are some number of years away from beaming that detector. Once the detector is built, it will be live for a couple of years before there's beam, in fact. But right now we actually have working 5% scale prototypes at CERN. So we are both a CERN experiment and a Fermilab experiment at the moment. In the foreground, this is the EH1 neutrino extension at Fermilab, at CERN. And you see proto-DUNE single phase, otherwise known as proto-DUNE horizontal drift. In the foreground, you see the dual phase, or what was a dual phase is now called vertical drift. In the background here, the beam is coming into the picture as you go. And that's not a neutrino beam at CERN, it's a charged particle beam, which contain pions, electrons. It can be tagged with protons also. So you can get the how liquid argon responds to all these various particles, and actually get interaction cross sections of all these particles in liquid argon too, which is needed. This is the inside of the vertical drift detector. We have 6 APAs out of the 150 that will be in a full module. We have 1 kiloton of what will be 17 kilotons of liquid argon in each of 4 modules. So it's still a very big experiment. So the DUNE collaboration was formed in 2015. It was, in fact, there were other long baseline neutrino things which merged to make it. Approximately 1,400 collaborators on 5 continents now, including Africa. Approximately 100 compute elements, 15 storage elements right now. As I said, we have a 5% scale prototype at CERN, which are already taking beam, and near detector prototype starting at FNAL this year to also take beam. 18 petabytes on tape already just from the test beam and the simulations. Similar to the total output of CDF ND0. So it's a very big experiment on FNAL grounds already. We already have some legacy software. So analysis preservation is already an issue for the papers we've already published. And we're making a full computing plan now for an experiment that has a long time for science. In fact, our compute design report is in collaboration review right now as I speak, and a lot of these plots are drawn from that. So the DUNE experiment will still be running at least 10 years from now, maybe longer. That's past the end of the Unix epoch. It's past the useful life of the x86-64 architecture. You cannot assume Linux will be there 20 years from now. You cannot assume grid computing will be there that long. Already, a heterogeneous architecture of CPUs and GPUs and FPGAs is part of our present, essential to our future. Will quantum computing be widely available by then? Or will quantum networking be available by then, maybe? We may need it by then, we'll see. So there are many similarities with an LHC experiment because we use many of the same underlying software tools and packages. We have a global collaboration with many different ideas on how to do things that are alumni of various LHC experiments. We participate and or observe in activities such as OSG, WLCG, HubCCE, Iris Hub, DOMA, from Ferrara, Ruscio. The full DUNE detector is expected to be about the same data volume as the current LHC Run 3 experiments that are just ramping up now. And we also have a distributed computing and storage element. But we're so-called the 400-pound gorilla. We're not quite as big. It should be said that all of those organizations above have welcomed us and wanted us to participate as much as possible, and we're very thankful for that. We do have some trouble actually getting bodies to be at all those meetings. A single proto-DUNE event is 130 megabytes, and we're rating at 25 hertz. A full fire detector event, if you read out all 150 APAs, would be 6 gigabytes at less than 1.1 hertz. Now, in practice, we will zero suppress heavily so that particles in the fire detector of DUNE will stop. They will not travel through the whole length of the fire detector. They'll stop in a few meters usually. Someday you will have a supernova trigger, and then instead of reading out for a few milliseconds, you'll be reading out the detector for 100 seconds, and you'll have to read out the whole detector. So that's the real challenge. That we will have a single trigger record, which is in multiple files that are segmented both by space and by time. Looking at what we have on already, which is just the small proto-DUNE detector, 75 megabytes compressed. LSC and SPP are only 2 megabytes per run. So where are we getting that much data from? Well, we're instrumenting a very huge volume at 5 millimeter spatial resolution. This is one-dimensional view of one anode plane assembly. So you're seeing time and it's a 3-dimensional view. 2 of them you get from space of 2 wire planes going different directions. The 3rd dimension is time. So the farther away you are from the wall, the longer it takes to get there. You have 12-bit ADCs. And so you effectively have a 2-dimensional plotting wire number against time. And this is as it comes in. This is raw data as it comes in on a display. You see also our signals bipolar, that the particle goes through the wire, makes a positive signal and then a negative signal. So there's signal processing here. That's in fact a very good candidate for GPU processing. Once you clean that up, remove dead channels, whatever, it looks sort of like this in single processing. Then you're gonna have to deconvolve it into make a three-dimensional tracks. So we're looking at a single channel here, and this single channel in one event got 1, 2, 3, 4, 5, 6, 7 hits. I note that proto-DUNE is on surface. So even though this was a beam event, there were a large number of cosmics in there as well. I'm saying very little about the near detector, but I note that our near detector is also on surface and will be of a similar volume, a little bit smaller than proto-DUNE, so we'll have to deal with this in the near detector as well. Beam is coming from the right in this drawing. We were able to find the one beam event in all of this mess. The other key thing here, there's no magnet, so there's no momentum resolution. We are measuring momentum because, like I say, all the particles are stopping. The detector is big enough. You have to tell the difference between electrons and photons. That's with this is so after we have the 3D reconstruction, then you have a final particle ID phase. You can tell the difference between all these various particles by ddx. And this is a big neural network case. You need a lot of processing power. This is a proof of concept that we did using proto-DUNE data. What we did is to set up GPU as a service on, this is a Triton service, Triton inference server. This is made by NVIDIA. This particular one we set up on Google Cloud. Passed through all of our good proto-DUNE data, around 60,000 files. They were already reconstructed at this point, and trying to identify Michel electrons, which are the decays of muons. Our conventional compute was at Fermi Grid. Our inference server was at Google Cloud, which the closest Google Cloud to us is in Iowa, about 10 milliseconds of latency away. For a while, we saturated the 100 gigabit site network link, calling back and forth there. So, but the particle ID phase, which would normally take a mean of 75 seconds to process, we get it done in 25. So it's a factor of 2 to 3 speed up using this type of thing. So there are clear wins for us at various places, both at the very beginning of the reconstruction thing and doing signal processing, and then at the end of the thing and doing pattern recognition, particle ID, etc. So we expect that GPU things will continue. Going now over to software management, SPAC is gradually becoming the building and packaging method being used, replacing the legacy Fermilab UPS UPD. It's taking a while for all of us to get used to it. It's not complete yet. We're learning how to read HDF5 format files, which are now being output by our DAQ. HDF5 is great for writing fast. We're still learning how to do streaming reads. Many of the multi-stream things that sPHENIX showed are happening in the DUNE DAQ as well, although not quite as big and quite as fast pipelines. There is a very similar ideas happening there. Within the past year, we've moved most of our experimental software repos to GitHub and implementing a pull request model with approvals. So the computing consortium is responsible for the software infrastructure, but individuals and detector groups are responsible for individual physics and detector groups are responsible for physics reconstruction algorithms. And memory footprint is always an issue. And we beat it down, and then they want more resolution, go lower. To give you an idea, if you're reconstructing a supernova, you're going to have electron tracks that are going at most a few centimeters each before they stop. And our physics coordinator says he wants to actually figure out how to point the supernova before we get out of the mine. In a couple hours, it's a very challenging process. So the unique framework requirements of DUNE, as I said before, we have several, but the idea is that the data can be split both in space and in time. So this is a very simplified thing of if I have just 3 APAs and 3 time windows. So I have to be able to look in APA 1, 2, and 3 in time window 1, 2, and 3. But in fact, in the supernova analysis, there will be thousands of time windows and hundreds of APAs. So this is a much more complicated thing. So we have to be able to deal with subsets. Fortunately, the problem is separable such that to first order, each APA can be analyzed individually and then combined later. But then we have to stitch it all together in the offline. So we are working on writing a new framework. The current DUNE framework is using ART, as many of the other Fermi-Lev neutrino experiments have used up till now, and RUT. There are, as you may imagine, very many databases that are used. We have, these are the 5 big ones, but there are others hiding out there too. Run conditions, beam, slow controls, offline calibration. But the architecture is to make a unified master metadata store and storing JSON blobs within that. So structured and flexible. But you can imagine when you're analyzing a liquid argon detector, you need to know what was the voltage, high voltage at any given time. It does go up and down. So there's a physics issue here. How granular do you make it? But for most circumstances, we expect the non-experts will only look at the runs conditions database, to which all of this is distilled down into a database that looks like a relational database on a run per run basis. This in turn can be accessed by Metacat, which is our metadata discovery service, which I'll come to a little bit later.
This is your 5-minute warning, Steve.
Oh my, hurry. This is a representation of all the various sites that we're running at. It's our goal to have only 25% of our offline computing at Fermilab, and to have as much as we can outside of the US. It varies from time to time. The US line is this whole part on the right. So we got quite a bit from NERSC at this time as well. We have allocations there via the HEP Cloud platform. We're designing a new workflow system. So we've always had the functionality and the legacy SAM thing to say, start my job, give me whatever the next file is of my project. But we're now going one step further to call back to the workflow system and say, I'm here. What's the best project for me to work on this site? And what is the closest, not only what's the next file, but what's the closest file to me network-wise? We have a number of sites that don't have a lot of network bandwidth in and out. So staging files close to where the compute is going to be an important part of what DUNE is doing, and also staging the output to where the DUNE is, to where the output is coming from is also important. So we have a proof of concept that we're going to be testing in the data challenge this summer. As I mentioned a couple times, SAM has sort of been the unified thing by which Fermilab has done data since the very early 2000s, developed for D0. It was a unified system, but we need a better replica manager because we have to deal with cross-Atlantic file transfers. It's our goal to have full set of reconstructed data in Monte Carlo on both sides of the Atlantic at any given time, and then we also have tape stores both at Fermilab and CERN. So Ruscio was the clear thing that was covered in great detail in the last forum. I'm not going to go into that. We need a hierarchical metadata system for more flexibility. That's Metacat. That's new, written by us. And then we need to preserve the project URL, delivery, and staging features that we have in SAM now, which is the data dispatcher. So a little bit more on Metacat. This is a diagram of the service. Our code base has been stable for more than a year. We're testing at scale now. Basically, the schema of Metacat was designed to be friendly to and compatible with Ruscio for replica manager. We were advised by the Ruscio developers at the time, don't use the internal Ruscio metadata to do this. User-defined scopes, a reserved field, hierarchical metadata. This is big, that you can attach metadata to a full data set, not just to each individual file. And then to query files based on Metacat plus external data conditions databases. So we're getting away from having to have voltages or leakage currents or whatever stored in the metadata, is stored in the conditions database where it belongs. The data dispatcher is currently in beta testing. Basically, it just keeps track of files in the project and when are they available for use, and to tell the worker node which file is the next one to process, and then the client tells the server when it's complete or whether it's failed. Briefly, this is our data pipeline coming from CERN to Fermilab for ProtoDUNE. In full DUNE, it will be very similar, except that the FAR data store will be at South Dakota. Ninja Daemon takes the file from the data store, transfers it by FTS3 transport to CERN EOS. From there, it's declared first to Medicat and then to Rusio. Those two are interlocked together, so you must declare to both. Rusio then handles the transfer of the data to tape at CERN and to Fermilab. And then from Fermilab, and also potentially from CERN, is spread out to our other storage elements around the world. Some challenges beyond high throughput computing. So we have a semi-infinite appetite for GPU and machine learning. There are several stages of doing software that are a good fit for GPU, but where do we get them from? Perlmutter and NERSC is one answer. Cloud is another answer. There is a highly constrained power budget underground, and there's limited space to put computers on surface. So we can't just build a data center and do it all on-prem. We have a high appetite for container and Jupyter-based analysis. Column-based storage analysis is already very helpful to some DUNE analyzers, but how do we keep it reproducible, loggable, and so forth? And there's two container-based analysis facilities already available. One is the EAF at Fermilab, and there's one organized at Canada by York University. How do we handle the extreme IO intensive merges, 150 to 1? Disk is getting bigger, but not faster, and even SSDs will not deliver the IOPS that we need. Tape robots are already a bottleneck, even at the scale we are now. Heterogeneous platform execution and validation. We've gotten soft from 20 years of Red Hat Linux and x86. The PAX Red Hat is over. We have to be able to execute and validate on a number of platforms and get the same answer. Data execution, environment preservation. So we've already published papers, we have to save the data. Same point, we have to make sure that we don't keep track of any junk data for longer than needed. How long do you keep your cold box test data, et cetera? If you're not careful, commissioning data can fill up a lot of tape in a hurry. And then how do we make it all friendly to mobile environments? So summary, we have unique challenges to reconstruct, simulate, and analyze our detector. We built a global computing consortium. We're making good progress in addressing many of those problems. We're grateful to members of our consortium, but also many others in the various laboratories who worked on solving these problems. And also thanks to all those in the various software communities and whose work we're building on, whose shoulders we stand. All right, thank you very much.
Thank you very much, Steve, for this really excellent summary with a lot of interesting things in there. Do we have any questions? I didn't see anything in the live notes. Any questions from the audience? I have a few then. So on slide 17, you showed how your reconstruction works, but how do you time in the various parts to ensure that you compare things from the same levels? Because typically at the experiments I'm familiar with, you have an accelerator clock, but I don't.
So there is an accelerator clock in DUNE, although we do not expect to actually trigger on it. The trigger system is meant to find out on its own whether the beam is running or not. Because underground, you can actually take every cosmic, and you will need to take every cosmic. So how do you time it in? There's a manifest, basically, or at least that's the plan, that the event builder, in addition to actually writing out all the various things, you'll have a trigger record code in each piece of the file that says this is all part of the same trigger record. You'll also actually have a manifest that says this file contains this many different pieces of this trigger record. In other words, we have we may very well have a time series of more than one event from the same APA and more than one trigger record. We're trying hard not to say event, but it's the habit from 30 years of HEP that you say event, but we're trying to call them trigger records, so that you have within HDF5, there are actually open source browsers that one can actually use to browse an HDF5 tree structure is actually quite handy. But so all the data files are tagged that we have this number, we have these parts of these events. And there's a manifest that's made that says this one trigger record is in these files, and this part of the thing is here, and this part of the thing is here, so you can go either way.
Okay, thanks. At the beginning of your talk, you made a statement that you do not assume that Linux will be around in 20 years or more.
Right.
Do you mean the particular Linux distribution version right now, or do you mean Linux
How old is Linus Torvalds? Do the math. He's not going to live forever. You think it will survive him? I don't.
Okay, so but
given the fact, given what we've seen with the last year of what Red Hat has done with CentOS and whatever, I mean, we're going to see a fragmentation. I think that the Linux thing must collapse under its own weight. I don't see how it can't.
But do you already have then a plan of what you?
No.
Okay, so and the something on the same slide when you mentioned that you do not expect Linux to be around forever. You mentioned quantum computing coming up. Can give some examples where quantum computing can play a role for DUNE?
It's a little bit premature, and I'm not sure if I'm bound by NDA on that.
Okay.
Good topic for about a year or so to invite us back.
Okay.
But the answer is yes. Given where quantum computing is now, and given some of the things that non-DUNE experiments are doing, non-DUNE work is doing at the Quantum Division of Fermi Lab, I think quantum computing will be a player by then. By the time DUNE sees beam, I think it will be.
Interesting.
Yeah.
Any more questions? Last chance to ask whatever you wanted to ask about DUNE, software and computing. I do not see anything. So thank you very much. This was really very, very interesting. Now we go to from neutrino physics to LHC physics. The last two talk about two LHC experiments and two very different LHC experiments. So the next presentation will be about preparations from LHCb. Rosen Matev will give the talk, and I'm very much looking forward to your presentation. Do you want a 10-minute or 5 minutes warning?
Yes, please, that would be useful.
Okay, I will give you both, and the stage is yours. So looking forward to your presentation.
Thanks a lot for inviting me. So indeed, I'll give you my perspective on how the LHCb Upgrade Restart is going on from a software point of view. Right. So first of all, very quickly, why are we doing this upgrade? So basically, in order to be able to do something useful with the 5 times the luminosity that we used to run with in the past, we need to upgrade the readout. We need to read out every single event, and in order to be able to detect displaced secondary vertices. This is the only way we can harness all of the rate that is in the order of 1 megahertz for CHAM, for example, at these low PT values that we're looking at. And just to give you an idea, this is the rates we're talking about is, okay, the LHC crossing rate is about 30 megahertz, and this would amount to about 5 terabytes, or at most 5 terabytes of data from our detector. And okay, obviously, I mean, we need to do this game because we allocated a limited amount of output bandwidth. So even if it's generous, I would say. Right. So how does the data flow look like from as a broad overview? So So you have the LHC bunch crossing, we have the full detector readout, and then this goes into the first stage of the reconstruction. So it's a partial reconstruction because not all of the detectors are used here. So this will be, well, this is implemented on GPUs, and this already reduces the rate from 30 megahertz to something like 1 megahertz. And this is then stored on a buffer, which gives us the opportunity to then align and calibrate the detector, sort of quasi real time, and then feedback. So on one hand, feedback the new alignment again to HRT1 to be used in the subsequent runs. So this happens on time scale, for example, for the Velo, which is closing every field, it happens on time scale of a few minutes once per field. And for other things, it takes a bit longer to collect the data that we need to calibrate. But most importantly, so then this feeds into HRT2. So for example, the rich detectors, they're only using HRT2, and we have time to calibrate them before we start. And then HRT2 runs on CPU and performs the full reconstruction, and has a lot more selections, physics selections, including exclusive signals. And so then this, so the exclusive signals, for example, go to this turbo stream, as we call it. So most of the physics goes there, in fact, in terms of rate. And then we have the full events, which also keep the well, the full all of the reconstructed objects in the event, all the raw data, more or less the equivalent, and we also have a stream for calibration. And then this further goes to offline. So from sort of the DAQ point of view, on the hardware level, this is organized in the following way. So we have the subdetectors, which are here on the top, so Velo, Reach, UT, so on. They are underground, obviously. Then we have these long fibers to the surface, and then all of the compute is in containers, in a little data center in 6 containers on the surface. So we have the readout units, which well, the servers which host the readout units. They also host the cards which implement this InfiniBand network for the event building, and they also host the GPUs for the HRT1. And then once HRT1 accepts events, they go over well, less fast network cards to the buffer storage, in some, which is implemented in some storage appliances, dedicated appliances, and then HRT2 feeds on these. So okay, so maybe you're not familiar with how LHCb is organized. There are obviously multiple projects inside for each subdetector. But there are also multiple software projects, in fact. So the oldest one, well, let's start with online. So online is kind of primarily hardware. It takes care of all of the things that I showed on the previous slide. So the networking, the storage that we need online, the event building, the servers, like the readout cards, a lot of things like this. But they also do a lot of software, and it's really important for us, well, for what concerns the rest, because at some point you need to run the HRT1 or HRT2 applications, and for this you need to interface with all of these things. But then, okay, so the computing project is probably the oldest one, together with online. So this includes core software, offline production, data management, things like this. So all of the tools that we have for testing, deployment, and so on. So something that is relatively new, so from 2019, is the real-time analysis project. So this And this deals with the high-level trigger, which has reconstruction, the selections, the persistence, all of that inside, also the alignment and calibration. And then we have a even newer project, which is again only on software, and it's called the Data Processing and Analysis project. And this is more oriented towards the offline side of things. So once the data is out into the tape storage, from there you have slimming, trimming, or further on you have user analysis, and the tools for that are developed within this project. And finally, we have well, the simulation is as an activity obviously has been there from the beginning, but recently it has been made into organized as a project as well. Okay, so I'm from the RTA project, so this will be biased heavily towards that. But if you have questions, I can try to answer. Okay, let me start with a quote from some young guy from the internet who says a prerequisite to writing good code is writing bad code. I fully agree with this. There's an important corollary here that we don't only have good code when collisions begin. So we cannot kid ourselves that we'll solve everything and there will be no bugs. And that's why we have to understand the system we're dealing with very well, so that we can sort of recover from issues. That's why it's really important to focus on tools, automation, and clear processes as we go along, not as an afterthought. So a little bit more concretely, so what is our release how do we change the code? What is our philosophy? So I split things here in two ways. So one in stable data taking. So towards the end of run 2, LHC run 2, for example, what we did was to cut a production branch each year as late as possible, but somewhere after data taking had started, we did that. And only fixes and localized changes would go into this branch. The rest, which was meant for future development, so for the next year or for the upgrade, this went into the main branch. For commissioning period, the strategy is a little bit different. So the plan is to maintain a single branch, and this is because most effort goes into actually running the system, trying to run the system, and there's a lesser expectation of stable output. So this is what allows us to be able to afford this, and also we kind of have to focus on the critical changes, and we can afford to postpone working on problems for the future. So in any case, what is really, really important for us is that we are ready to release, let's say, the production of the main branch at any point in time. So, one really important thing is that we have a solid framework. So the modern Gaudi, I won't talk about the details, but the modern Gaudi or the way to use it in a modern way ensures that it's very hard to introduce thread safety issues unless you start, cons casting and things like this. It really guards you from doing stupid things. An important thing is obviously good test coverage. So we have some unit tests, but mostly we're focusing on integration tests. And we have a code review that if we're merging something that is really critical, then we make a point to do this thoroughly. What do we test? So all of these things usually happen on every merge request. So we use GitLab. So we have merge requests. There is a so-called nightly build system, but it's not nightly anymore because it happens on every merge request, which can be any time. But this obviously compiles and runs unit tests, and runs the integration tests on a few events. As part of this, you check some functionality of, for example, for the persistence. Can you write data? Can you read it back? in the various formats we support and so on. Any change in performance, so for the reconstruction within a certain tolerance, it needs to be blessed. So you need to somehow understand it if it happens.
You have 10 more minutes.
Thank you. So there's another thing which is performance and regression testing. So these are tests which take longer and need dedicated resources. So there we test throughput, reconstruction performance on a more global scale, rate efficiencies and so on, things which can afford our operations. Okay, then switching to actually how we run this online. So Gaudi online from a very, very far looks like this. You have some events on input, you have the trigger, for example, and you have some events on the output. A few events. Like looking more carefully, it looks like this. And so there are a lot more inputs and outputs if you think about it. And okay, there are many different use cases and applications which you might want to run. And so if you rotate it a bit to read it, so there is the steering of the application, you have conditions, you have options and configuration. So these are related. There is the software that you actually want to run. Well, the steering again is an output because you can receive the application can generate some events. There's non-event products, there's monitoring, there's logging. So okay, let me skip that. It's not very interesting. But what are non-event data inputs? So the software mostly comes from CVMFS in the online infrastructure. This is a local cache for each node, which is good. It's quite like scales very well, obviously. And there's a bit of NFS. So NFS could be a problem. And it has been a bottleneck in the past. In run 2, what we had is about 1,500 nodes running HRT2, and each had something like 30 processes on average. And this is because we were not running multi-threaded, we were running multiple processes because our application was not thread safe. So when you try to start HRT2, suddenly there's 50,000 processes trying to read from the same files from NFS at the same time. So this obviously is some contention and it's not optimal. In the future, we mitigate this by having better NFS and fewer processes because we run multi-threading. Of course, you can do different things, but as I mentioned also below, for conditions, NFS is really convenient because it's simple files. So in terms of configuration databases, so this trigger configuration, weights, various things like this, again, CVMFS. So for things which are generated by the run control, so conditions, for example, as output of the alignment processes. So this goes via NFS, and the same caveats apply. The pros that it's very simple to use NFS overweight the cons by far, I think. And the steering happens over sockets. So this is more or less how things look like in one, or let's say in two nodes. So on the left, you have a picture of the architecture of one HRT1 node and one HRT2 node. So you have a process which receives the data, a process which HRT1 which processes data, something that sends the data out to monitoring or writes the data to a buffer. For HRT2, you have something that reads from the buffer, the actual HRT2 processes, something that sends the output out. So on the right, you have the final state machine, which is something that is implemented kind of on top of Gaudi. So there were recent developments in Gaudi which allowed to do this more naturally, and so so these behaviors can be implemented on top of Gaudi, and you don't have one monolithic event loop as you would have in an offline job, but you can actually feed events. So let's say one at a time, you can stop processing, and you're independently controlling the process. So zooming in on the sort of data moving between processes. So this is implemented with this buffer manager process. So it's yet another process which basically owns some shared memory. So the events, the producer declares events to the buffer manager, and the consumer consumes events from the buffer manager. So it's a concept that actually is applied everywhere, basically. So it's pretty flexible. And so within the obligation, well, I won't go into detail how the event is accessed, but this is a bit Gaudi specific. So in terms of non-event data outputs, so monitoring, so logging is kind of monitoring. Nominally, you should use it only for debugging. In the past, we've had a lot of expected messages, and this kind of numbs you, and you start to pay less attention about what you get in the logging. So you should avoid that if you can. In terms of monitoring, we need it for several reasons. Quality control is one. Is the trigger configuration okay? You need some feedback, but also data quality, because the detector can misbehave very often. So we should check that. So debugging issues, real-time data for the LHC. They request some sort of measurements from us on luminosity, on beam position, things like this. And we also need to record this for ourselves in order to do simulations later.
We have 5 more minutes.
Thanks. So in terms of trigger output, so the only thing I want to say is that the data that the format that we use online is really simple. It's events which can be concatenated one after the other. You can cut them obviously between events. So it's not the route where where it's very difficult to stream in this way. But it's this very simple format that we have. What is really, really important, so there are many pieces which go together. So what's really important is to have a test bench that allows you to iterate really fast when you develop this. Because when you first try to put everything together, there are lots of problems. So you start discovering issues in the tools, issues in the actual thing that you want to run, and so on. So you want to get to a point where you have reliable tools with which you can iterate fast. And just running in the full-blown experiment control system is not the way to go, because it takes you probably order of 10 minutes to start an application and get some feedback. This simply is not workable. So spend time on tools and test benches. So for HOT1, I mentioned that it's on GPU, so it needs some kind of, therefore it needs a bit more work, and in order to integrate it into the system, it processes the data in a slightly different format, because this is the format that comes out of the readout units, where the data is grouped by sort of by kind of front end and not by event. So that's why it's different, but otherwise we try to pretend it's basically like a Gaudi application. We wrap it into a Gaudi application actually, and modulo the event loop, it basically behaves like one. So you can steer it the same way as HOT2. You can obtain geometry conditions and so on in the same way as HOT2 does. You deal with changing conditions and so on. Monitoring is the same. One important thing to note is that this runs on the event building node, so you have to be really careful about CPU and memory usage, and this has been the subject of basically extensive tests in order to decide on actually going for this solution. And finally, on the test beam that we did in October, so the LHC performed excellently. So they often go faster than expected. So maybe it has also true in other cases, not only the LHC. So be prepared, basically. We've had things happen 2 days in advance of when they were initially announced, which is nice, I guess. The LHCb ran with a few upgraded subdetectors. Not everything was in place at that point. But overall, it was really successful. So so the online system was kind of commissioned. It was demonstrated to work. The detectors which participated were time aligned. The monitoring system and the visualization tool was sort of used and integrated and used. And even HLT1 was able to process data. So it ran on CPU and GPU on a mixture actually, because this is what we had installed. And it ran in pass-through mode and in activity mode. So it triggered based on calorimeter activity. And here just a couple examples. On the right, you have this demo of HLT1 actually selecting some events, reducing the rate. And on the left, you have a demo of the rich rings. And just a few takeaways. So I think communication is crucial. So with detectors and among software projects, you've seen we have many software projects, and we have to coordinate always, like that the simulation produces the data format that the reconstruction expects, and so on and so on. So the main things to coordinate. You have to share infrastructure as much as possible. So the fact that we could run monitoring tasks and produce these plots, this was thanks to the work that we did on HLT2. And thanks to the fact that they are really similar, they're Gaudi applications which behave in the same way. With software, you can do most of what you need remotely. However, you need such live sessions. I think it's really important because, well, beam time is a strong motivator. 1 year before beam time, okay, you know it's coming and you're working on it, but somehow the urgency is different. And also it brings people physically together. We suffered from this a lot during COVID. But yes, I think it was really nice to do it in person. And when there's no beam, you can try to organize hackathons, and we do commissioning weeks and so on. Yeah, I mean, obviously there are a few things which you only see with real data. So for example, we had one example where some data padding was not implemented according to specification on the reading side. This was obviously not seen in Monte Carlo, and there were crashes because of this. The channel mapping, the conditions may not correspond to the real cabling, which is again something it's only you can spot in real data. And there's always more that you can wish for in terms of how you can test and what you might want to do. Thank you.
Thank you very much. This was super interesting. We have time for a few questions. Running a little bit late, but not too late, so questions are possible. Let me shortly have a peek to the live notes. If no, I don't see anything. So can you go back to slide 22? So something which I always try to emphasize in some talks is really the community aspect of software. And you really made this point about it's how important to bring people together. Can you give some examples where really being in the same room helped, other than having, let's say, a gun sheet or something where deliverables are listed?
I think it just helps you iterate really fast on things. I mean, it's simply like gun sheets or other ways to organize yourself, which are asynchronous like this. They don't work when you want to debug something on a schedule, right? So obviously you can try to do it over Zoom, but somehow I think there was a lot of the feeling that there's a common problem that is being solved, and there's a common cause, and people were really happy about making the progress they made. I mean, even if it was not like a huge progress, even if it could have been done offline or before even you started doing this sort of commissioning, the fact that it was done when people were present, I think, made them feel very good about it, and increases the motivation going further, because this is not the last thing you need to do. I mean, this will go on for at least another year. So I think this is where it's just creating a nice atmosphere of work and keeping the motivation high.
Thanks. You have in LHCb enormous amount of expertise and experience with GPUs. As far as I understand, your whole Allen system is purely based on GPUs. To what extent do you use machine learning in your algorithms?
Oh, I'm not sure about that. I think we do use some inference in the trigger, which is selecting based on 2 tracks, so displaced versus based on 2 tracks. But I'm not sure exactly which model is used and what inference.
Thank you. Last questions for or last chance for your question on LHCb preparations. I don't see anything. So thank you very much again for this very interesting talk. So let's come to the last talk of today, Software and Computing Roundtable. And we will hear from we started with heavy iron. We will go back to heavy iron, and David Rohr will give us an update from Alice, and I will share the slides on behalf of him. David, are you ready?
Yes, can you hear me?
I can hear you very, very well. Do you want to have a 10 or 5 minutes warning?
I have 20 minutes, right? Because then there's 5 minutes.
Yes.
I have a clock here. I don't need it actually.
Okay, perfect. Then let's get started.
Next slide, please. So basically I will start with some introduction to what Alice is doing and how Alice is getting the data, or how Alice is seeing the data. So challenge for Alice in run 3 is basically heavy ion collisions, because that is what Alice is made for. We also take proton-proton data, but heavy ion is the big deal for us. And the main tracking detector of Alice is the TPC, so the time projection chamber, where you basically have overlapping collisions inside the drift time. And that is what you see in the background. So the background is an illustration of how, well, 2 milliseconds of heavy ion collisions in the TPC will look like. And you see different collisions in different colors, and you see that they are overlaid basically in the Z coordinate, which is along the drift time. So that is the data that we are getting. And now, obviously, we don't get single collisions, and we cannot disentangle the data in the TPC between the collisions before we do the full reconstruction. So we cannot reconstruct single collisions or single events, but we have to reconstruct the full data at once. And this is what we call a time frame. So a time frame is just the total data that we get from all the detectors over a certain time period. And what you see here is 2 milliseconds, and the processing in reality it will be more like 10 milliseconds. And this also changes, of course, a lot all our event building and scheduling, because we don't have to send events around or build individual events and then build chunks of events for better utilization of GPUs or something, because single events don't have enough parallelism. But we have these large timeframes which are processed at once, and this is the unit that we process. And that basically also solves all the scheduling issues, because the timeframes are processed at a rate of, well, around 100 Hertz. So only 100 a second, so this is quite easy to schedule. The second big change for Alice is that we will not do any triggering anymore, but we will store all the data, because the signals we are looking for, they are quite rare and they have a large background. So this is really difficult to basically filter it online. So we want to store all the data, but of course this is a huge amount of data, because we will have 50 times more collisions and thus 50 times more data than before. So we do online compression of the full data. And since this is computationally quite intense, we use GPUs to speed that up. Can you go to the next slide, please? Yeah, and just to give you an overview of the Alice detector, I don't know how familiar with it. So basically this is looking at the barrel region and only at the tracking detectors. There's also calorimeters and fast interaction trackers. So going from inside out, we have a silicon detector with 7 layers of silicon pixels. Then we have the TPC that I mentioned before. So the main tracking detector was the drift time. And then we have a transition radiation detector and also a TOF detector that can also be used for tracking, but particularly for calibration. And can you go to next slide? And yeah, the calibration is something that is quite important for the TPC, because this is a drift detector. So I will spend, well, a few sentences on that. But let's look at what online processing does ALICE do. And online processing basically serves two purposes. So the first is data compression, as I said before, because we have to reduce the data size since we now have 50 times more events. But the second is also calibration, and calibration is of course done for many detectors, but the most complicated calibration is for the TPC. Because in the TPC, we now have the problem that the TPC is a drift detector where we have the ions drifting. And since now we have 50 times more collisions and the amount of ions obviously goes linearly with the collision rate. So we have 50 times more ions in the TPC and they produce an electric field which distorts the electrons during the drift time. And there's a quite complicated procedure to basically correct for these distortions created by the space charge inside the TPC. And that needs tracking and track matching of TPC tracks to the inner and to the outer detectors. And that means for the calibration of the TPC, we have to run online tracking. And then because we use a track model compression for the TPC, we also have to run online tracking for the data compression, which means the two main steps for the online processing is data compression and calibration, but for that we need tracking. So we have basically full online tracking. So that is what we do online. And then of course the offline processing, what we call asynchronous processing is the standard thing. So we just do full reconstruction, having the full calibration available. Can you go to the next slide, please? Yeah, just to give you an overview of the computing hardware that ALICE has. So we have split the readout and the processing basically in two computing farms. So the first farm is the FLP farm, first level processor that you see on the left. That is 200 servers with FPGA cards that receive the optical links. And then the processing happens in a GPU farm, which is equipped with 2000 GPUs in 250 servers with 8 GPUs each. This is called the EPN farm that you see on the right. It stands for Event Processing Nodes. Next slide, please. And now I want to guide you a bit through the data flow. So we get the data via the optical links from the detector in the cavern. So that comes up from the cavern to the counting room 1, CL1, to the FLP farm at a rate of 3.5 terabytes per second. Now in the FLPs, we have the FPGA cards and they do a first very simple local compression using mostly common mode correction, afterwards zero suppression. At first, we want to do the zero suppression on the readout in the cavern, but this is not possible because the common mode correction needs to be done beforehand, and that needs access to multiple links, so it can only be done in the FPGA. But okay, so this is quite simple compression, and this reduces the data size to around 600 gigabytes per second, and that this is the input to the GPU computing farm, where we do the full tracking and then the calibration and the data compression. And with that, we get the data rate down to a manageable 100 gigabytes per second, which is written to storage. And then from the storage, it's replicated to the tier centers, and to basically we need multiple replicas. And okay, can you go to the next slide? So yeah, and we have a scheme that is quite similar in some sense to what LHCb is doing. So we have what we call synchronous processing. That is what happens during the beam. That is more or less what LHCb is doing in HLT1, except for that they are triggering and we do compression. I mean, in some sense, both is reduction of the data rate, and it's running online on GPU. So it's from the approach, it's similar, but okay, we are compressing and they are triggering. But then, as I said, data will go to a disk buffer, and after the data has been stored there, and when there is no beam in the LHC, we also have what we call asynchronous processing. So can you go to the next slide, please? And in the asynchronous processing, we read back the data from the disk buffer and do a reprocessing of the data. And now this can happen partially in the online computing farm, so the EPN farm, but also partially on the grid. So we have the on-site disk buffer at the farm, which is used there, but the data that is sent to the tiers, of course, can also be reconstructed in the grid. And the asynchronous processing is more or less what was classically the offline processing. So we don't have something like an HLT2. Everything that is stored to the disk buffer is basically the raw data that we have. We have no triggering, as I said. So the asynchronous processing is just the classic offline processing. Next slide, please. Okay, and then I want to spend one slide on the GPUs because GPUs are quite important for the ALICE reconstruction. And so, okay, I was speaking a lot about the TPC for calibration and for compression in the online processing. And in fact, the TPC makes up for, well, more than 95% of the total compute power that is spent basically online. And this TPC processing was very well suited to run on GPUs, and therefore we have decided to use GPUs basically as the backbone of the online processing. And that is more or less the baseline solution. So we do full TPC processing on the GPUs, And then part of the ITS, so the silicon tracker, we also do the GPUs because we already had that. Okay, but now we are in a situation where we have the GPUs in the online farm, and we use the online farm also for offline in this asynchronous processing. And around 90% of the compute power in the online farm is actually from the GPUs, not from the CPUs. So it would be quite a waste of resources not to use the GPUs for the offline processing as well. And that is why we are doing basically a quite big effort to port as much of the software as we can to use GPUs also for the offline processing. And the idea is to have basically a consecutive chain of reconstruction steps on the GPU, such that the data can remain on the GPU, and we can just offload one set of, or let's say one connected part in the reconstruction chain completely to the GPU. And what we have selected for this as best candidate is the tracking chain, so the full tracking of the barrel region, including all the detectors that I mentioned before, so ITS, TPC, TOF, and TRD. And that is what we call the optimistic scenario, basically, where we would use the GPUs more or less to the full extent also in the offline processing, at least when the offline processing runs on the EPN farm. Of course, we also have the offline that runs on the grid, and that will be CPU only for the time being. So this plot, I will not go into detail, but it shows basically the full tracking chain, and you see the steps of the baseline scenario and of the optimistic scenario, and you see in green what is already running fully on the GPU. And yeah, basically everything that belongs to the baseline scenario is running on the GPU, and we have been using that in the pilot beam. And this is working, and we are working now more towards bringing more stuff on the GPU also for the asynchronous processing. Can you go to the next slide? So, okay, here, I just want to quickly flash this. I think one important thing when working with GPUs is that you want to be independent of the vendors. So you might want to buy different GPUs maybe for your next HLT farm. So maybe you want to buy a different model then. And also you want to test all your code on the CPU. So you want to make sure that this very same code runs on GPU and CPU. So I think we have kind of a generic framework, which we have created ourselves some years ago when we started with that. If we would do it now again, probably would use something that is available. But yeah, the idea is that we have one common source code that is shared between CPUs and GPUs, and then we just have small wrapper codes that bring the common code to the GPU. So if we change something on the algorithm, we only have to change it once, and we do not maintain different code bases. And we support CUDA, we support OpenCL, we support HIP, and we can run on the processor with OpenMP. So next slide, please. Now I'm coming a bit to how we test this before we go to the experience that we have from the pilot beam. But of course, we want to do a full stress testing with Monte Carlo data. And particularly, we want to test for heavy ion data, because we have only 3 weeks of heavy ion per year, basically. So we need to have a full stress test for the heavy ion, such that we do not do stress testing while we take the data. We must be ready beforehand. And the strategy we have here is what we call the full system test. So full system test means we take one server, basically. The reason that one server is enough, that we have the event building, and then we send the full, in our case, it's basically time frame building. So we send the full time frames to the servers in, well, some more elaborate round-robin fashion, basically. And then a server processes a time frame. So we have completely separated, in that sense, the reconstruction from the event building. So this full system test is only testing the reconstruction. But we are looking at one server, and we are feeding it with a real readout process, basically with data at the rate that we expect from the 50 kilohertz LED, which is the design luminosity. And then we can see that we can do the full online processing at that rate, and we measure the memory consumption and the CPU load during that time. And okay, here you see a plot. So we need, in average, 40-something CPU cores with a peak of 44. We have 64 cores per node, so we have some margin there. And then you see that for the memory, there's different buffer types. I'm not going into detail, but basically there's a burn-in phase at the beginning where the buffers are filled because we fill the pipelines. And then at some point, we process the events as fast as they're coming in the pipeline, and the buffer utilization is stable. So this shows that we can fully process the expected peak LED rate using the computing farm that we have. Okay, next slide, please. And now I will come a bit to the pilot beam, but first of all, just as disclaimer, so we don't have physics results to present, so I will also not show any plots. So what I'm showing here is basically my personal perception of how the pilot beam went, because I was heavily involved in the commissioning and in the operation. But I mean, this is not official ALICE results. This is really just how I see it, because otherwise I would need to go through a lot of basically bureaucracy to get this published. So next slide, please. Okay, so the thing is that the pilot beam is, of course, for ALICE quite different to what we will be doing in the end. So we were designed for heavy ion at 50 kilohertz. Pilot beam is PP at few kilohertz. So even less interaction rate than heavy ion. So computationally, it's not inexpensive. It's basically zero. So there's no compute load for the real reconstruction. However, we have to see that some detectors have a constant load, like the TPC has a certain noise, which must be processed in any case. And okay, since the pedestals were not optimal during the pilot beam, this was actually higher than what we will have hopefully in the end. But so actually processing the noise was more compute load than the processing of the data itself, at least in the TPC case, because we have the continuous readout. So we basically read out all the data, but we only have few collisions, and so all the everything else is noise. So this was actually not zero processing, but the real data would be zero processing. So that is the first thing that is really a bit, I mean, it makes the pilot beam not a real benchmark for what we are doing, because if we would scale any result like buffer utilization, throughput, CPU load from the pilot beam, we would basically scale what we need for processing noise, not for processing the data, and that is absolutely not relevant. And yeah, I think the second, and that is already kind of a conclusion, I would not call it experience from the pilot beam or lessons learned, because I think everything that we learned again, because we probably saw it again, what we saw in Run 2 commissioning. So we should rather call it like reminder, because okay, Run 2 commissioning is several years old. Some people have changed. So I think it is important to note down the lesson that you learn in the pilot beam and really use it again for the next commissioning. Next slide, please. Yes, okay. And then the second general comment is that one should start global commissioning as soon as possible, because what we basically saw is that you have many issues that are considered irrelevant by the people because they occur only every couple of hours, and then you restart and you think you're done. But then you have 20 systems when each of them fail, well, occasionally, but the total system then will fail multiple times an hour, and then you cannot all the time restart it. So I think it's really important to start global commissioning as soon as possible. And whenever there is a problem that can affect a global run, even potentially, and particularly if it's from a central system that you cannot disable like a minor detector, then this should be investigated immediately and solved. Okay, but so coming from the global comments more to the software standpoint. So ALICE in the pilot beam, we were basically doing two things. We were recording the raw data. This is just because we had so little data, so we could record all the raw data, and this makes sense just for future tests on this data, so we can replay them and do everything, and we are just safe. But we were also running the full online processing just in parallel. So we were creating the processed, compressed data and the raw data. And the surprising thing for me was that this online processing was completely smooth. So there were, I mean, we had some issues, but like really it was extremely smooth. The issues were not at online processing, they were somewhere else. And I had expected many issues with the online processing because this is really different to what we had done in Run 2. Beforehand, we had a readout, and the readout does not touch the data. So this does not show data-driven problems. Maybe if the headers are corrupt, okay, but if something is bad in the raw data, the readout will not care. You will see later in offline tracking. But for us now, since we do full online tracking, if there's something bad in the data, we actually expected that we would crash. And yeah, it's quite important actually that you do not crash, because we are not an HLT where you can switch off, let's say, a trigger for something, or we do the compression of the raw data, and if we don't compress the raw data, we cannot store it. So basically, the online processing for ALICE is mandatory, and yeah, it went better than expected. Although, as I said, we had some issues. I think we had like maybe around order of 10 issues where we had something where a bug of reading raw data, or I mean, some corrupt raw data or whatever caused crashes, and we could fix them basically all in short time. And the important thing is here, you need some kind of rapid development. So you cannot do something like weekly deployment of software as you do for readout only, because then you will just not be able to catch up. And of course, there must be some compromise with respect to stability. You cannot update the software every hour, but I think you need rapid development. Next slide, please. Yeah, and so what we did, and I mean, we are still discussing the final scheme for the development and for the deployment of the software, but I think what it will be in the end is something like this. So we can have multiple versions of the software installed in parallel, and then we can separate the full ALICE experiment in multiple partitions of detectors, and different partitions can use different software versions in parallel. So we can, for instance, have a global partition that runs some golden software, which is well maintained and stable, and we update it only weekly, where we are quite sure that it works, but it might not have the latest features. And maybe if something is broken in that partition and we know it, in that software and we know it, we don't exchange the software, but we just disable the broken feature for that one. And if someone wants to test that feature, then you have to use one of the other software versions that installed. And then we install on a daily basis or even on demand new optional alternative software versions that can be used by standalone tests and also by detectors in parallel. And this basically extends the CI. I mean, we also have, in the same way as LHCb presented, a CI that runs on every pull request. In our case, it's 5 LED events, which corresponds to 500 pp events, I think, from the data size. But this is, of course, not representative for raw data, because if you really process data as it's coming in, you have much more data and you're exposed to much more statistics. And you have the online behavior, of course. So this allows us basically to test new software versions online on small subsets of detectors. And if we have an issue there, we get it reported immediately. And this extends the CI. Okay, next slide, please. Okay, and then I think, as I said before, we cannot learn much for processing rates from the pilot beam. And one example is that I actually tried to create a plot with GPU processing speed for the TPC of the pilot beam data, and I did not find a reasonable way to publish that, because when I try to explain what is happening in the plot, because the plot looks so bad because the pilot beam doesn't have enough parallelism, my explanation would have been, okay, we have this plot, but this plot is not relevant because there is not enough parallelism. If you want to look at a reasonable plot, look at this Monte Carlo plot, which shows something that is realistic and that matches the data that we will have. So I think the pilot beam data, this was really good for stability testing, but it's not good for any rate estimates, and it cannot be used for extrapolating the rate to something that we will have in the real run. However, one important thing I want to mention, and this will be the second to last comment, is that a big opportunity that came with the pilot beam that we could run not only the online software, but also the offline software basically during the processing. So we could enable steps like TPC DEDX, which we usually only do offline, but we had so much spare capacity because this was so little data that we could run a lot of the processing steps just online. And because we have the software framework where we have the same framework for online and offline, and we just switch on reconstruction steps, this is just a flag and we put it in, and then we have the offline running online and get like online DEDX. So this was really nice. And okay, so the last comment is that a big caveat that I see with the pilot beam processing is that many things were created under time pressure, under the impression like pilot beam is zero processing, so we can find some random workaround, put it in place, and it will just work for the pilot beam. This worked, but the problem is some of them are still in place for PP now, and people think, yeah, maybe it will work for PP and we have to replace it only for LED. And I think this is the wrong approach. So you have to develop the software for the real rates, not what you have in the pilot beam. Okay, next slide is the conclusion, but since I ran out of time, I will just leave you with that. Thanks for the attention.
Thank you very much, David. This was super interesting, and a lot of fascinating things in here. Are there questions for David's talk update on ALICE? Well, I have a lot of questions, so let me ask a few of them. You mentioned on slide 9, when you talked about heterogeneous computing, that you develop your own system, and from what you showed, it works remarkably well because you have one source code and then you can deploy it on various GPUs. But that if you now would do something differently, what would you choose now if let's say you would start this development today and not a few years ago?
Well, I think I would look into the frameworks that are available, even commercially or academically, that do basically what we did. And I think it doesn't make sense to reinvent the wheel every time. I think these generic frameworks, they are not so complicated. I mean, in our case, it's just a few thousand lines of wrapper code, maybe 2,000-3,000 lines. So this, I mean, it's not really hard to develop or really hard to maintain. But I think still, if someone else is doing this for you, and maybe also then you get the expertise and the ideas from other people working on the same field. Yeah, but okay, since we were not doing this, I basically didn't look into so I couldn't tell you which candidates would be promising for us. But I mean, something like Alpaca or something, but really I have no idea. I would need to dig into in detail.
and if I have seen your overview plot correctly, then you have already a lot of your process in production running on GPUs, but some of the things where there's work in development are the calibrations. And of course, this is a very difficult problem because you have a TPC, which is not a priori a super fast detector. You have these many overlapping heavy ion events. But is there any prospects, or are you planning that, having your calibrations completely autonomous?
Well, I think you have to separate it, but the calibration is basically 3 steps. We have reconstruction that produces some calibration input. That is the first step. The second is merging and pre-processing of these calibration objects into something that can be digested by the final calibration step. And then you have something that gets all this input and creates the final calibration output. And I think the computationally intense thing in most of the cases is actually the first one. So that is part of the reconstruction. And that is already running online, and that is running partially on the GPU. I mean, I have it on the summary here. We have at the moment 95% of the synchronous processing. I mean, if you just take the workload, you measure everything on the CPU, you just see how many CPU hours you spend for which task. The 95% of that is running on the GPU already for the online thing. And so that is basically everything. There's no need to offload anything else because we have some spare CPU resources. And for the offline, we are at the moment, I mean, it depends a bit on how you measure and what hardware you have, but at the moment we estimate we will have 60 to 85%, and if we do some more work, we can get to 90. That is the goal. And this does more or less not include the calibration. There's one special calibration where it would maybe make sense, but this needs to be investigated because this calibration is still under development, and this is this TPC space charge distortion calibration that I mentioned before, where we also use some machine learning and some inferencing, and that of course is something that would be suited to run on GPU by design. But yeah, this is still in the development phase, and we will have to see. The problem is a bit that we also run on the grid, so we could not do something that requires a GPU. It must run on the processor, except for the online. The online can run fully on the GPU. Everything else, of course, should run on the processor and should optionally use GPUs if available.
Okay, thanks. That was helpful. Last chance for questions to David. A lot of material here. All right, then thank you, David, for the very interesting talk. Thanks to all speakers for today's contributions. So this concludes the Software and Computing Roundtable of April. We will continue on May 3rd, and then our topic will be workflow and workload management systems, where we have presentations. I will go in alphabetical order from Dirac, Panda, and Parcel. Thank you very much for tuning in today, and see you latest in May. Thank you very much, everyone. Bye.
Thank you.
Bye.